Okay, with that, we're going to move on to a presentation by Roger Janssen, President and CEO of 3DX Industries. He's going to talk to us about additive manufacturing and uh, basically the process, what that looks like, some of the qualification. It should be an exciting discussion. And with that, Roger, I'm going to make you the presenter. Are you ready to go?
Yep, Alexander, I am.
We'll just put
Okay,
this.
with that, um,
I'd
yeah.
like to thank the SME community for inviting us to talk about 3D metal printing, which I can talk about for hours. And much like robotics, it's there's a lot of opportunity, and I'm going to go through and talk about what we do, how our process works. I have many sample parts that have interesting stories, so I can help everybody understand how this process works. It's a binder jet process, and we're going to start. You know, as far as the industries, additive manufacturing is, we have a diverse customer base. So, we have aerospace, we have medical, there's dental, there's commercial goods. There's a lot. The beauty of additive manufacturing for us in 3D metal printing is we can have 10 different customers' parts in the build box, and they can be all different industries, and we can process those parts at the same speed. So with that, I'd like to get into how our process works. I see our PowerPoint up here. Okay, great. Is that the start first?
Yep, looks great. You can go full screen too if you need on the PowerPoint.
I'm working with Nick Coriano here, my VP of East Coast Operations. We'll go to the first slide. Yeah.
Which way you want to go? This
Yeah, there we go. So that's pretty much, those are some fun things we do. If you'll notice the aircraft there, that was printed for a P&A event that I went to many years ago. I handed those out. It was one of our first projects that we printed. Made a small jet airplane. But yeah, a varied industry. It's varied throughout the industry of many. Yeah, it has lots of applications. And this covers a little bit. I'll run through some of the slides here before I get to some of the parts on the table afterwards. The part that has the little trigger on it, that's a needleless injector for medical industry. The parts right above that, that's for microsurgical, I believe, in Bellevue area. It's a part that helps them manufacture surgical components for eye surgery. The part to the left of that is a piece of tooling for the Boeing Ever plant. The part left to that is for Janicki Industries. That was a part that went on the Omni processor that Bill Gates helped them build. The part to the left of that was a very unique prototype. I don't recall the industry, but of course below that there's pump impellers, turbine blades, and talking about end of arm tooling, the piece in the middle of that, there where Nick has the pointer, that's an end of arm tooling for a robotic arm. So many different processes there. Now the market opportunities, these are current numbers. As you can see, the industry has been growing. As we know, 3D printing is becoming more of a mainstay of supporting all the manufacturing. And that's what positions 3DX. We're pretty excited about it. To back up a little bit, we started looking for competitive edge back in 2010 at the IMTS show when I ran into this process. And we had been plastic printing since 2007, but I found this process, and in 2012, the company that we purchased the equipment from, X1 out of Pennsylvania, that next year I sent them so much work, I ended up being their largest industrial supplier. And it was interesting because, as you can see, since then, that's been probably 8 years now, 8 or 9 years. The industry continues to grow and the opportunities are also growing. You can see some of the numbers there. Auto part industry is looking, very competitive. You can change. It's helped bring that back from the, it's going to allow us with binder jet technology to come back and reshore a lot of parts. So there's a lot of reverse engineering going on. There's a lot of DFAMs in process. We're doing many for several of our customers. And because of now the cost of 3D metal printing, the speed, the machine, the ease of use, we're able to get competitive with part prices. And a lot of creative engineers are helping us bring that along also. So a little bit here, it talks about the market opportunity, projected growth rate. Here's a number of businesses that are currently, we found that are using that. A couple of the companies that are looking at 3D metal printing. They're building it. HP has gone to binder jet machines. Materialize is supplying software. 3D Systems, I think, has a binder jet machine. Desktop Metal recently acquired X1, and they're going to be doing a big push on some new binder jet machines. So it's here to say is what I'm saying, and it's going to be a very good tool going forward in manufacturing. So now I'll go through our process a little bit here. Here's the machine that we use. We have two of these. They're the X1 M Flex. Their build box is a part that's like 10 by 10 by 14 inches in our build box area. And now we'll walk through kind of how the process works. This is a build platter. So what we're doing is we're using 30 micron stainless steel powder, and we're spreading that layer by layer. So that's about 3,000ths of layers that we're currently set up is our resolution. You can go down, that's 30 micron. You can take it down. It's a trade-off for time. So we like to
powder really quick.
Yeah, the powder.
Yeah, stop the share. We'll show them the powder.
Oh yeah. So this is quite heavy, but this is 30 micron stainless steel powder. That's what that looks like. It's kind of like talcum powder. Get that in the camera there a little bit. Bottle weighs about 30 pounds. But so we coat that layer by layer, and then we have a precision print head that has 1,100 print jet nozzles that are controlled by little piezo. You guys probably know that better than I do. It's the engineering side. They're little valves that so accurately deposit the binding agent. Then we spread a layer of metal powder about 3,000ths thick. Then we bind that together, and you continue on until you've done the whole box. You continue to repeat the steps until you go the whole 10 inches on the print box. Now, the interesting thing is we can print about 1 inch of powder every 4 hours. Now, in that 1 inch, we can have one part or we can have 1,000 parts. It depends on what the part configuration is, of course. So that allows, if you want to say how fast can it print it, it depends on the part, of course, but that's how fast the machine goes with whatever you can fit in there. So once the print process is complete, the build box, it's a stainless steel box, is removed from the equipment. It goes into a curing oven where it cures at about 6 hours at 385 degrees. And what that does is the binding agent consists, let's call it like an epoxy. And in that heating process, that epoxy then hardens up. So you can take that part and then you remove that box from that curing oven, and you can remove those parts. It's like an archaeological dig. You're digging through the powder, and you can pull these parts out and you can handle them. They're still in the green state of that part prior to the final sintering operation. So then they get packed in a carbon crucible, and they go in, and we have parts we're using here. It's a stainless steel bronze mixture. It's called 420 stainless bronze. And we put that through the sintering oven. It takes about 24 hours in the sintering oven at 2,048 degrees. The parts come out, we post-process them, then you end up with something like this that's obviously known as a dog bone.
Show some parts.
Yeah, let's show some parts. We have some finished parts here. This is a great one here. If anybody's into the saxophone, this one here is a machine saxophone out of solid brass. And these two are 3D metal printed. This one is zircon plated. Theo Wani is a local guy. He's like world renowned for his saxophone mouthpieces. So he was here. What he's excited about in the saxophone is he wants to change the way the wind blows through the saxophone mouthpiece. But in order to do that, the machining cost is much too high. So he says with 3D metal printing, he wants to design different ways to have the wind flow through the saxophone mouthpiece so he can get new sounds. That's something that's we're able to design and build turbine rotors that could never before built. I mean, this is a cross section. You guys can see that. That's a turbine rotor. And this is actually what got us into this industry is we were machining these. I chromed these because these are my two flagship parts, but this is what kind of got us into 3D metal printing. Now, these were a sheet metal stamped and welded assembly with a CNC lathe part. I think our costs was around $800 in assembly for this. 3D metal printed, they were around $150. And the same thing on this one here had quite a high machining price because of the small grooves on it. And we brought the 3D metal printing price down by a multiple of 4 on that part. But that helps the engineers. You're able to design things without the restraints of thinking, geez, this thing's going to cost so much, or I have to have a sinker EDM, and I have to have a wire, and then machining. It's a different way. Like they say, complexity costs you 0 is one of the taglines they like to use in 3D metal printing. But
Slide.
yeah, let me go another part or two here. So here's a downhole oil drill part that previously was made out of 4140 steel, and they power this down the drill body. And what they found was this is a high wear part. So this part is 2,000 feet down the surface. It's driving a drill module, and they would wear out. So they'd have to pull it back out and replace it. Now, using the 420 stainless bronze material, this part lasted 5 times longer down in the depths. The cost was about the same for manufacturing, but their gain was just the increased product life. Because, with 3D metal printing now, you have a whole new ability to bind different materials together that aren't like off the shelf. You can put the chemical composition of that material is almost unlimited at this point. So you can actually engineer a part with the properties you want, and they'll build you a material to make it work like that. Yeah, I'll go back to the slide where we were. So in the turnaround is 3 to 4 days. We can take a part from your CAD model and process it through printing, curing, sintering, and most parts require some machining afterwards. It's still hard to 3D metal print small threads. And if you have a datum that has a tolerance of a flat datum within a few thousandths, and it's you would add 10 or 15 thousandths of material to those datums, and you take them over to the machine shop and you machine them off. We're already at the rework slide here. Mm-hmm. Okay, one of the questions that was brought up last time we talked was, how do you handle rework on the 3D metal printed parts? And I was thinking that through. The material welds well, and you can make some modifications to it and fix it. But one of the biggest beauties we found after doing a lot of production, if you take a typical part here, these are parts that we're making right now. The part in the middle is hogged out of that block of stainless steel 304, and we're defamming these parts for our customer right now. But as long as that part has not been into the sintering oven, we can still recycle it. So we print that while it's still in the green state. If we notice a defect or something that we don't like, we can grind that back up and we reprocess the powder, and you can reprint it. So if something doesn't look good. So what my point was I'm trying to make with this photo here is, if you had to rework the part or remake another one, what would you rather do? Take another block of stainless to make that one part because you're 3 short on an order of 100 pieces, or you just grab the powder and make 3 more. It makes it quite simple that way. So here I have a recent test from Mistras, which is a big testing company. They're here locally with the refineries. We're next to a few refineries up here in Ferndale. But that gives you some of the chemical compositions and the pull test on this from the engineering standpoint. I don't know how clear that is, but we just recently had them. They took a part very similar to this one, and here's the results on that. So as far as testing the materials, there's RCAM, which is actually a laser sintering machine. It's a little bit different than the binder jet process, I'm sure you know. They have over 250 new qualified materials that they're using on laser sintering machines. And for binder jetting, we have, you want to move to the next. Okay, thanks, Nick. This currently from the factory, this is what X1, they have successfully printed in these different types of materials right now with binder jetting. So the trade-off between binder jetting and 3D printing or laser sintering, I like to use the example. The cost factor on the average, I'm going to say, is 3 to 1. I can binder jet parts much more cost effective than laser sintering. Now, that being said, some parts are laser sintering. They're going to be, for that process, laser sintering is going to be the way to go. But if you can figure out a way to binder jet them, your part price is going to be much, much more competitive. So, and along with this also, this is the qualified materials from the X1 company. Most people that are buying their binder jet machines are qualifying their own materials. We have 2 materials that we worked with a company called NanoSeal that we developed with them. There's called the J10 and J11. There are two versions of stainless steel. One is a very tough, hardened stainless, and the other one's much softer. So as far as qualified materials, the interesting thing from the engineering standpoint is the sky's the limit. I mean, there's constantly new types of materials coming out, which allows you to make a different type of part or use a different material to make that part. Excuse me. So, okay, let's go off to simulation here. So one of the areas in binder jetting, there's a lot of simulation software out there now for laser sintering. And now that binder jetting is really taking a stronghold and getting some traction, there's a couple companies. This is a photo from Sigma Labs out of New Mexico. They've been tossing around some different software versions to help with the binder jetting process. It's very young in the development stage, and there's a lot of, we need some smart people to come in here and help figure this out. And just one example, I'm going to go switch to a part here to explain some of the problems that we've had here. So this part is an exhaust manifold for a heavy lift drone for Amazon. So they came to us and they wanted this part machined out of either titanium or 3D metal printed. So we 3D metal printed this part, and this was part number 2. You can see some of the fractures on it. This is part number 1. We had some failures on this. We ended up printing this part 3 times to get one good exhaust manifold. And it has a small turbine motor on it. This drone delivers, I think it's a 75-pound package with a 50-mile radius is what they're working on. But my point being with the software is the opportunities there for somebody to help develop this software to a better, we wouldn't have had the 2 failures. This was unnecessary the way I see it, because these prints are about 30-hour prints for these bigger parts. So I think we have a little bit more on the simulation side. Now this here is showing everybody's seen the picture of the laser welding, the laser sintering parts, the materials, the micron steel parts together. Here we have, like, let's just call it 30 micron, the little balls, and it's the droplets. So the key in binder jetting is the droplet size and the accuracy of the droplets. That's where you get the quality of your part. And it's all the race between speed and how fast you can drop those droplets accurately. And this is just one of the simulation softwares out there that's trying to help, make that a better product for sure. So, and in a nutshell, guys, I could talk all day long, but I wasn't sure where we're going to be at on this. We have thousands of parts here at the facility that we have printed. We have shelves and shelves of interesting prototypes. This part here is oh, I'm going back to parts already. This is with Samson rope here. This part went to Newport News on a special rope that they're designing, a special hook. It is quite interesting. This is for, we did many hundreds of these. That's I don't know how well that will zoom in. That's a K-Pod cup for an industrial coffee pot. And the interesting thing about this was we had to add material to each one of these little points because they couldn't print sharp enough. And then we would machine them in the CNC machine. And we had a process. They would machine to razor sharp in about 45 seconds. We were able to finish that part. This here is a security screw bit for Panasonic Aviation. So that the challenge here was it had to be a hardened bit with a security screw piece on it, but each one had to have a different serial number because they serial number these and assign them to the mechanics. So quite easily done in 3D metal printing, very hard in the machining world. There's some watchmakers out there that are using 3D metal printing. This is a binder jetted watch because it's a little wind piece, the bezel face, little tiny holes in it, but you can see some of the intricacy that we can do with a part like this. So that the sky's the limit on development. Go through another one here. So a typical part, customer comes through the door with this piece here. This is out of a World War II tank. It's a drain that goes on the bottom of the tank, and it's cracked. They want a new one. So we reverse engineer it, we plastic print it, and this will be one of the next jobs that we print. And it's going to go on the bottom of the tank they're restoring. It's kind of got a little plunger on it, the valve. They step on it at the bottom of the tank, lets the water out. But yeah, in a nutshell, guys, that's binder jet 3D metal printing. And we're excited. There's a lot of opportunity. The reshoring has caused a lot of activity for us. And we're going to have a great year. We're looking for the best of the best. We're looking for people that want to work with us. We're looking for partners. We work with the University of Bridgeport. We have an office back there in Connecticut. We have an intern program. We have some patented parts that they're working on designing, and we're having them design those parts with additive manufacturing in mind. And that's what we're looking at a lot of our parts, because it's a more cost-effective and interesting way to make our parts, and it's faster to market, and we can do it here. So we're kind of excited about that. Another part, this is a fish slicer for Alaska General Seafoods. Now these parts, the prints for these parts, we still get them. They're actually blue. They come to us. They're designed in the 1930s. And this part was designed, you can see the radius on it. The way they said to machine this part originally was out of a pipe. Then they lay them down and they flat powder them. But this is a perfect example of a one-off part that we can print. That if you had to make one machining, it would be a lot of work. This would be a downhole tool part for Halliburton. You can see a little bit of the radius. This holds a box of electronics that goes down the hole of an oil well and reads some materials, gives some data on that hole going down. And I was wanting to mention too, I just saw in the news that the Department of Defense just awarded some 3D printing contracts for the Navy. And one of them, we've worked with Keyport. Keyport out here has had one of the original binder jet printers from X1. It's probably over 15 years old, because we've had the tech out here working on our machines that worked on theirs. And he'd tell us little stories about what they were making. And one of their projects was they were making hand grenades out of different shapes so they could find them in the dark, depending on what style of hand grenade they were looking for. But they were constantly using that machine, and I still believe it's out there, still working. So yeah, there's a lot of interesting things made with that. But other than that, I don't know, is there anything I'm missing, Nick, what these guys need to know?
No, I think we can open up to questions.
Yeah.
One of the things we definitely wanted to mention before, we open up to questions is that we're definitely looking for interns, very enthusiastic about, recruiting the best of the best, and whether that means interns, whether that means professionals. And we've actually opened up a remote internship program. So we understand that some of these COVID implications are here to stay. And we also know that the best engineers aren't always in your backyard. So partnering with the University of Bridgeport in Connecticut, literally on the other side of the country, was kind of our testing ground for that. And it's worked out marvelous. We have the first internship program, and they're going to have a hackathon next semester, all focused on creating some of our patent portfolio. So we're really excited about any students that could potentially join our team. So open it up to questions.
Yeah. One other quick shot. One more thing I wanted to show. Most of us here get Modern Machine Shop, but if you look at last month's edition, there's a great article on an additive manufacturing machine shop. It's a medical base. I'm quite partial to this because they use the RoboDrill machining centers, which we use here. I love them. I'm biased, of course, but they're fantastic little pieces of equipment to do the second post-processing on additive manufacturing. But it's a great article if you got the current Modern Machine Shop. But yeah, with that, I'm happy to answer some questions.
Roger, I'm going to jump in there right off the bat and say thanks. That was so cool.
Seconded.
Second, we're in your backyard. I've got about 4 engineers right off the bat, future engineers. We've got to get connected with you because they were so into this sort of concept. They did some research themselves. But let me ask you a technical question. I'm talking right now about in the design course, the materials design course, about all the vast universe of things to choose from. And the things you just talked about, those materials, one, their material properties are different than the standard material properties that are out there. So how does someone in a client of yours start off finding the material specifications for things that don't exist yet. I mean, we're in the industry, I can go and use Grant and other databases to find the materials I need and be able to box my constraints. You're telling me you're using stainless steel bound with other bronze or other type of binding, end state binding agents, which means the material properties, both axially and longitudinally, are different than other crystal grown materials. Where do I find this data? Where does the customer find that?
It's interesting, Bill, that the data on that, it still seems to be under some hats depending on everybody's racing to get their proprietary material.
Yeah.
And there's a lot of them that are out there. And the ones that I showed you the list of are from X1, and those are the ones that are available. That list is much bigger if you saw the inside list from their customers that they're working to develop new materials with. Now, that being said, I have access to those and the ones we worked with NanoSteel that was bought out by Formetrics. We have all the data on that material for designing. Now, as far as the other materials, I think if you went and bought an RCAM laser sintering machine, every material you want to add, it's called qualifying a new material. So we've looked at the laser sintering machines. We will end up with laser sintering machines. We see the opportunity for them. But every time you qualify a new material, it's a $50,000 software upgrade. So, you got it. And that's for the ones they qualified, but there are engineers that are working on just developing new materials. I know one, it's Harold Lemke is working with a faster company, and they're buying a binder jet machine just to develop new materials for fasteners. So that's kind of something that, I guess to answer your question, there's not a list available like that, but there is information available. And if you want to develop one, I'd be happy to work with you and do that. So,
well, it's so fascinating because the classic world, they're going to go off to a certain class of material to work their design.
yes,
You're telling me that if I can combine these metals in a new alloy, I've got a new game, and because you manufacture them not through some sort of hot work process to the degree that it's, there is a hot work process part of it, but you get my point. There's a different game. You're playing a different game.
absolutely.
I guess toss back in your court. We've got a cluster of projects or non-projects that if you're looking for some basic college level test on some of these things, you can toss them our way, and those become a project for the capstone students, just testing some of your new materials in those designs you just spanned out there. So not to say it's free work, but it's one of those fun things where it's a mutually beneficial. I think everybody gains for trying to help you take some of those new toys you've got and say, hey, go bust this for us because we don't have the time right now, but I know half a dozen college students could get us some data pretty darn quick.
Yeah,
Athletes spend late hours doing it. Hey, Bill, could you drop your information in the chat for them
Will
to?
do.
Okay.
I was just thinking about how much fun it would be to work on a thesis related to the simulation software and fine tuning. I'm guessing it's a CFD project or a CFD software.
Yeah, I'm not real familiar with that, how that goes together. That's a little bit out of my wheelhouse on that, but I see a lot of people taking stabs at it. I know Materialize has. They've been here looking into some of our challenges. I know some people are racing to find the software package. The software we're using, of course, as we use it on a daily basis, I think, if we tweak this or if we had this option or if they really could work this in somehow, I can see a lot of opportunities for making changes to make the process better.
Yeah.
Well, I had a question for
Sorry.
both of you guys too, if I can jump in. First of all, thank you. Once again, to our members, we have two high-level executives, Roger, better part of a decade, president, CEO of a publicly traded company, leader in the field, and his VP as well, Nicholas. Thank you both for spending time with us today. If I could get top 2 or 3 qualities from each of you guys of what your ideal candidate coming in out of school would be. I heard some reverse engineering skills and maybe 2 others.
I think the design for additive manufacturing is an interesting one. Though there's a lot of examples on the internet. If you go look at some of the brackets that was traditionally machined, and then they've used the software to completely analyze, it looks completely different. And we have a customer that we machine a lot of stainless parts, and they're going to allow us to defam all those parts, and it's quite a project, really. But once we start getting that figured out, it's going to be a much better way to manufacture those parts. But the defam, I would say, would be a good one. Understanding many of the different additive manufacturing technology. You have electron beam welding, you've got laser sintering, and of course binder jet. There's a couple other around the outsides that are hovering around that may be a winner, it may not be, but it's the jury's still out on that. But just being aware of those technologies when you're looking at building your parts, I would be somebody that I'd say is, would be really valuable for us and be a lot of fun.
Yeah, I'll add to that just two kind of traits that I look for. Curiosity, like an endless curiosity, is definitely one trait, and entrepreneurial. We're a very entrepreneurial company. If you look us up, we're a small public company, a growing public company. So there's a lot of potential for curious, energetic engineers to come here and take a hold of a project or a division as we grow. So those are the two things that I look for.
Those are great. And one other thing I thought of as you were talking, strength of CAD skills. Where would you put that out as far as expertise goes?
Yeah, I think your standard SolidWorks, we're obviously SolidWorks users. The CAD skill on that, as far as additive manufacturing for us, every one of these parts has an infiltration point on it that you have to be, you might have to add that infiltration point to the base geometry once you have your part designed. So you need to have a knowledge of the printing process and be able to manipulate that geometry to add that infiltration point to where it won't damage the part in the process. So I think the CAD skills for that are a good SolidWorks base, and you're good to go.
I found the same skills were necessary in the foundry world, taking incoming models, making them casting friendly.
There you go.
That's good to hear the same's in additive. So that's something we can translate the curriculum though on the student end pretty easily. Thank you.
Guys.
Yeah, my pleasure. It's good being here.